Hello student, I am Dr.A.K, Professor of Chemistry. Today I am going to discuss new chapter, that is the chemical equilibrium. Last time I have discussed, last class I have finished completely thermodynamics. Now I am going to start chemical equilibrium. It is a very important chapter. Actually all chapters are important because from every chapter questions are asked in examination, and not only that, these chapters, all chapters has also important in real life also. Then here chemical equilibrium. Chemical equilibria are important in numerous biological and environmental process. Chemical equilibrium, also called chemical equilibria, are important in numerous biological and environmental process. For example, equilibria involving oxygen molecules and the protein hemoglobin play a crucial role in the transfer and delivery of oxygen from our lungs to our muscles. Similar equilibria involving carbon monoxide molecules and hemoglobin account for the toxicity of carbon monoxide. When a liquid evaporates in a closed container, just try to understand. When a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. Means in a closed container you have taken a liquid, then liquid molecules will escape because its kinetic energy is more, and it will go to the vapor state. In vapor state, as for example H2O, many H2O are joined to each other by hydrogen bonding, that's why they are liquid. Then these H2O bond will break, hydrogen bond will break, then it will go to the vapor form. And again from the vapor form, after some times, it will come back to the liquid. This here you have to understand. H2O molecules from the liquid, it gone to the vapor state, means only H2O, no hydrogen bonding, only H2O, that is called vapor of water. Vapor of water. Then after some times again this H2O will come back to the liquid. Then see how liquid is going to the vapor, and again from vapor it is coming back to liquid. Here this is the important things, but these things it is happening in a closed container. Then these things you have to understand here. When a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure. Because of an equilibrium in which the number of molecules leaving the liquid equals the number of returning to liquid from the vapor. We can tell that the system has reached equilibrium state at this stage because molecules went from liquid to the vapor state and again it came back from vapor to liquid state. When sufficient molecules from the liquid went to the vapor and when molecules become large number, then again it will come back. Then going to the vapor, from vapor coming to the back. That is called equilibrium state. However, this is not a static equilibrium. Equilibrium is of two types. Okay, here one is a static equilibrium. Other is a dynamic equilibrium. A static equilibrium is also called mechanical equilibrium. Mechanical. Then what is the difference between these two, static equilibrium and dynamic equilibrium? Static equilibrium actually on the molecules will feel zero force. Each molecules will feel zero force. When all molecules feels zero force and they are not moving, then it is called static, S-T-A-T-I-C, static equilibria. What is a dynamic equilibria? Then in dynamic equilibria, molecules will be in motion. And reactant and product, reactant side and product sides, okay, their mass will not change. Means reactant and product, reactant to product, product to reactant. They will be coming and going, coming, like that way. Then everywhere same concentration. And that time pressure will not change and temperature will not change. This is the very, very important things. At a dynamic equilibrium, concentration of mixture, actually in equilibrium position, whatever reactants are there, mixture of the reactant and products will be same. That is called equilibrium mixture. Okay. In equilibrium mixture means mixture of reactant and products, and both from reactant it is going to product, that is a forward reaction, and from product to reactant, reverse reaction, also called backward reaction. Then rate of forward reaction and rate of backward reaction becomes equal. This is the characteristics of dynamic equilibrium. Just like you can tell from one pipe water is coming. Then if it is coming in a same speed, you can't see that water is moving. And you will feel that it is just that water is fixed. You were feeling like that. Suppose pipe is made up of glass, transparent, suppose. Then you can see that water is static. But it is not like that. From one end, water is coming. From the other end, it is going. Then see, this is not a static, not a stoppage. Movement is there, but it looks like that. It is stopped. But it is not like that, not a static. Then in equilibrium, that from reactant to product, it will be going. Forward reaction, backward reaction, both will be going. Okay, going, coming. And rate of forward reaction is equal to the rate of backward reaction. And reactant and product concentration will be the same. And from the any end, reaction can be started. from the reactant end also or from the product end also. And this equilibrium, sign equilibrium, already told you, that is the double arrow, double half arrow, double half arrow. Arrow is full arrow, no? The full arrow. Here half arrow. Double arrow will be one from reactant to product, half arrow. Okay. Both wing will not there, only half a wing. Now forward, again from forward to backward, one arrow, half a wing. Okay. This I have told about the dynamic equilibrium and difference between a static and dynamic equilibrium. Equilibrium can be, just example I am giving first, that H2O liquid and H2O vapor is the best example. H2O liquid to the H2O vapor. Okay, you can't see that when you will see liquid always will be converting into vapor, vapor will be converting into liquid. Then this vapor molecules will create pressure on the liquid. Vapor molecules will create pressure on liquid, then liquid surface. Then that pressure is called vapor pressure. Vapor pressure, because from liquid molecules are going outside. Again in atmosphere, again it is coming back. Actually, whose energy will be more? Suppose it is opened, not closed, open, then all vapor will go. It will not return. But it is in a closed vessel, then vapor will come back. And that time these vapor molecules will create pressure on the liquid surface. Then that is called vapor pressure. Okay. Then H2O liquid to H2O vapor means liquid vapor equilibrium, you can tell. The double half arrows indicate that process in both directions are going on simultaneously. Okay. The mixture of reactants and products in the equilibrium state is called an equilibrium mixture. Equilibrium can be established for both physical process and chemical process. Okay. Two type of chemical process are there, physical process or chemical process. Then this H2O liquid to H2O vapor, this is example of physical process. Okay. Means liquid to vapor, vapor to solid, solid to vapor, correct? And vapor to solid, already I told you. Then these are the examples of, you can say, physical state. Liquid to vapor, vapor to liquid, liquid to solid, solid to liquid. All are the examples of, you can say, physical state. Then I told about the equilibrium can be established for both physical process and chemical reaction. The reaction may be fast or slow depending on the experimental condition and the nature of the reactant. What type of reactants are there, whether it is a solid or liquid or gas. When the reactants in a closed vessel at a particular temperature react to give products, the concentration of the reactants keep on decreasing. Here very important things, that when reaction will start, when the reactants in a closed vessel at a particular temperature react to give products, the concentration of the reactants keep on decreasing, while those of products keep on increasing for some time, after which there is no change in the concentration of either of the reactant or products. Because When reactant converted to product, and quickly it will convert this product, again it will convert to reactant to product, product to reactant. This process will continue, means both process, backward, forward and backward, it will continue. Okay. After sometimes there is no change in the concentration of either of the reactant or products. This stage of system is the dynamic equilibrium. This stage of the system is the dynamic equilibrium, and the rate of forward and rate of the forward and reverse reaction become equal. It is due to this dynamic equilibrium stage that there is no change in the concentration of various species in the reaction mixture. This is happening due to the dynamic equilibrium. Okay, now I am telling about the based on the extent to which the reaction proceeds to reach the state of chemical equilibrium. Extent I am talking about, extent to which the reactions proceed to reach the state of chemical equilibrium. There are three groups. You can divide it into three groups. Extent can be divided into three groups. Okay, these may be classified to three groups. First, you can say all three groups are in equilibrium, but extent you can see how much. Extent means how much, what percentage. First, you can see the reaction that proceed, the reactions that proceed nearly to completion and only negligible concentration of reactants are left. 99%, more than 99% reactant converted to product. Okay, when it converted to product, then again product will give reactant. Okay, first extent is that the reactions that proceed, the reaction that proceeds nearly to completion and only negligible concentration of reactants are left. In some cases, it may not be even possible to detect these experimentally. Okay, means maximum reactant converted to the products, means reaction is going on. The reaction that the first category, the reaction that proceed nearly to completion and only negligible concentration of the reactant are left. Okay. Second, the reactions in which only a small amounts of product are formed. Only a small amount of products are formed. Reactant were more, but product form very less. Means extent is very less. Okay, very less converted to products. The reactants in which only a small amounts of products are formed and most of the reactants remain unchanged at equilibrium state. At equilibrium state, two conditions I told, both at equilibrium state. Now third extent, the reactions in which the concentration of the reactants and products are comparable, means both are almost same, reactant and products. When the system is in equilibrium, means system established, equilibrium established, but reaction in first case I told you that maximum converted into product and again product began to convert to the reactant. Okay, and second case only less product was forming, but they were in equilibrium. Reactant were there, but they got equilibrium also, but all not converted into the product. Third case, reactant and products were comparable, means almost same. Then this I told extent of reaction. Okay, the extent of reaction in equilibrium varies with experimental conditions. Why all have not converted into product? Why all reactant has not converted to product? Why less converted? Correct? Then this extent, why this all product, all reactant is not converted. Sometimes some reactants are very less reactants are remaining. Most of them converted to the product. Third case I told comparable. Then what are the reason? That reason I am telling you. Okay. The extent of reaction in equilibrium varies with experimental condition such as concentration of reactants, temperature, pressure, etc. Okay. Optimization, actually this action depends upon concentration of reactants, temperature of the reaction and pressure of the reaction. Optimization of the operational condition is very important in industry and laboratory. Where it is used this extent, then it is used in industry and laboratory. This condition, operational condition is very important in industry and laboratory, so that equilibrium is favorable in the direction of the desired product. Means what condition is required so that you will get the desired product. That time it is useful. Okay, then many you can say physical process are there. Then example I am telling you, physical phase transformation is the best example. Phase transformation process. As for example, solid to liquid, equilibrium between solid to liquid, liquid to gas, and third, solid to gas. Okay, first example, equilibrium between solid to liquid. Second example, equilibrium between liquid to gas. And third example, solid to gas. Okay, equilibrium between solid to gas. Okay, then here I have told you about the, you can say, phase transformation process. Here again little more things you can know. Example, for example, ice and water. Ice is solid, water is liquid. It is obvious that ice and water are in equilibrium only at particular temperature. This is very important. They believe in equilibrium are only at particular temperature and pressure. If anyone will change, then they believe not in equilibrium. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal boiling point or normal freezing point of the substance. Again, you listen carefully, this is important. It is obvious that ice and water are in equilibrium only at a particular temperature and pressure, correct? At a particular temperature and pressure. Now you understand, for any pure substance at atmospheric pressure is okay, constant, the temperature at which the solid and liquid phases are at equilibrium is called the normal boiling point. That temperature is called normal melting point or normal freezing point of the substance. The system here is in a dynamic equilibrium because water is converting to liquid, water molecules are converting into liquid, liquid molecules are converting to the water. That's why it is in dynamic equilibrium. The system here is in dynamic equilibrium and we can tell or we can infer the, you can say, two things we can tell. First, we can conclude, first thing, both the means first things we conclude that both the opposing process occur simultaneously, means water to liquid, means ice to liquid, means solid to liquid and liquid to solid. Both the opposing process occur simultaneously, not like first you can say solid will convert to liquid, then liquid will come to solid. No, both we can tell, we can conclude that both the opposing processes occur simultaneously. Second conclusion, both the process occur at the same rate. That's why mass of reactant and products will be the same. Both the process occur at the same rate, so that the amount of ice and water remains constant. Then I have given you background of, you can say, chemical equilibrium or about the equilibrium. Today I am stopping only here. Next class again we will meet. Okay, thank you.